The cosmic puzzle, when you look up at the night sky, it feels endless. Stars glitter like diamonds, galaxies glow faintly, and the universe seems filled with light. But here's the shocking truth. Everything you see, every planet, star, and galaxy makes up less than 5% of the universe. The other 95% is invisible. Astronomers call this hidden part of the cosmos dark matter and dark energy. Dark matter 27%. The mysterious glue that holds galaxies together. Dark energy 68%. A strange force that is pushing the universe apart faster and faster. Together, they dominate reality. Yet we don't fully know what they are. Imagine reading a book where only the first 5 pages are visible and the rest is blank. That's how our understanding of the universe feels. The discovery of dark matter, the story begins in the 1930s when Swiss astronomer Fritz Zwicky studied a group of galaxies called the Coma Cluster. He noticed something odd. The galaxies were moving so fast that, based on visible matter, the cluster should have flown apart. But it didn't. Something unseen was providing extra gravity, holding the cluster together. Zwicky called it Dunkelmaterie, dark matter. At first, the idea was ignored. But decades later, more evidence arrived. In the 1970s, American astronomer Vera Rubin studied the rotation of spiral galaxies. She expected stars near the edges to orbit slower than those near the center, like how planets farther from the sun orbit slower. But instead, she found that stars at the edges moved just as fast as stars near the center. This defied the laws of physics unless something invisible with enormous mass was surrounding galaxies, giving them extra gravity. Once again, dark matter. Evidence for dark matter. Today, we have multiple lines of evidence that dark matter is real. 1. Galaxy rotation curves. As Rubin showed, galaxies rotate too fast to be explained by visible stars and gas alone. 2. Galaxy clusters. Zwicky's observations still hold. Clusters need unseen matter to stay bound. 3. Gravitational lensing. Einstein's theory of relativity says mass bends light. When we look at galaxy clusters, we see background galaxies distorted more than expected. This distortion reveals hidden dark matter. For cosmic microwave background (CMB), the faint afterglow of the Big Bang contains patterns that only make sense if dark matter exists. In short, dark matter is not just a guess. It's a measurable phenomenon, though we cannot touch, see, or directly detect it yet. What is dark matter? So, what exactly is dark matter made of? We know what it is not. It's not stars, planets, or gas clouds. We can see those. It's not black holes. There aren't enough of them to explain the mass. Instead, dark matter seems to be something completely different, possibly new kinds of particles. Candidates for dark matter. WIMPs, weakly interacting massive particles, the most popular theory. Hypothetical particles that barely interact with normal matter, making them almost impossible to detect. Axions, tiny, lightweight particles that could fill the universe like a background fog. Sterile neutrinos, a type of neutrino, a ghostly particle we already know exists that interacts even less than normal neutrinos. MACHOs, massive compact halo objects, things like faint stars or black holes. But observations suggest there aren't enough MACHOs to account for all dark matter. The role of dark matter in the universe. Dark matter is not just a curiosity, it is essential to the existence of galaxies, stars, and planets. Imagine trying to spin pizza dough without enough flour in the center. The dough would fly apart. Similarly, without dark matter, galaxies would simply not hold together. Dark matter forms enormous halos around galaxies, spherical regions of invisible mass that extend far beyond visible stars. These halos act like cosmic scaffolding, allowing galaxies to form and stay intact. In fact, computer simulations of the early universe show that without dark matter, the universe would look completely different: diffuse, structureless, and lifeless. In other words, without dark matter, there would be no us. The expanding universe. At the start of the 20th century, astronomers thought the universe was static and changing and eternal. But in 1929, Edwin Hubble made a groundbreaking discovery. Galaxies are moving away from us, and the farther they are, the faster they recede. This meant the universe is expanding. For decades, scientists assumed gravity would eventually slow this expansion. Maybe the universe would keep expanding forever at a slower and slower rate, or maybe it would one day stop and collapse back in a big crunch. But what came next shocked everyone. A surprising discovery, 1998. In the late 1990s, independent teams of astronomers studied Typea supernovae, exploding stars that shine with a predictable brightness, making them excellent standard candles for measuring cosmic distances. By comparing their apparent brightness with their redshift, how much their light is stretched by expansion, astronomers could calculate how the expansion of the universe changed over time. The results were stunning. Instead of slowing down, the expansion of the universe was accelerating. Something mysterious was pushing galaxies apart faster and faster. This invisible force was named dark energy. What is dark energy? Dark energy is not like anything we know. While dark matter pulls things together with gravity, dark energy does the opposite. It pushes space apart. But what exactly is it? 1. Cosmological constant lambda. Proposed originally by Einstein in his equations of general relativity, represents a constant energy density filling space itself. Could be vacuum energy, the energy of empty space. 2. Quintessence, a hypothetical dynamic energy field that changes over time, unlike a constant, similar to how electric or magnetic fields permeate space. 3. Modified gravity. Perhaps our understanding of gravity is incomplete on cosmic scales. Maybe dark energy is just a sign that Einstein's equations need an upgrade. Right now, we don't know which explanation is correct. We do know this: dark energy dominates the universe. The evidence for dark energy. The case for dark energy comes from multiple independent sources. Supernova observations, 1998, the original discovery. Cosmic microwave background (CMB), tiny fluctuations in the afterglow of the Big Bang only make sense if dark energy exists. Baryon-acoustic oscillations, patterns in galaxy clustering across billions of light-years confirm accelerated expansion. Large-scale structure. The way galaxies are distributed and moving today reflects the influence of dark energy over billions of years. Together, these create a consistent picture. The universe is not just expanding, it is doing so at an accelerating pace. Dark matter versus dark energy. It's important not to confuse the two. Dark matter has gravity, pulls galaxies together, forms cosmic structure. Dark energy works against gravity, pushes the universe apart, drives cosmic expansion. One binds, the other tears apart. It's a cosmic tug-of-war. Right now, dark energy is winning. The fate of the universe. The presence of dark energy dramatically changes the possible endings of the universe. Scientists consider several scenarios. 1. Big freeze most likely. Expansion continues forever. Galaxies drift farther apart. Stars eventually burn out. 2. Big rip. If dark energy grows stronger over time, it could eventually tear galaxies, stars, planets, even atoms apart. The universe would be destroyed in a final catastrophic rip. 3. Big crunch. If dark energy somehow reverses or weakens, gravity could eventually win, pulling everything back together into a fiery collapse. This seems less likely with current evidence. Why dark energy matters. Dark energy is not just a curiosity, it is the driver of cosmic destiny. It determines whether the universe will live forever, die in fire, or fade into silence. It challenges our deepest understanding of physics, forcing us to rethink space, time, and energy. And perhaps most intriguingly, it reminds us how little we know. We like to think of science as having explained most things, but the truth is 95% of the universe is still a mystery. The search for the invisible universe. How do we hunt something we can't see? The challenge of dark matter and dark energy is simple yet daunting. They don't emit light, they don't absorb light, and they don't reflect light. In other words, they are invisible. But scientists are clever. Instead of looking for them directly, they study their effects on visible matter. Just as wind is invisible but can be felt in the sway of trees, dark matter and dark energy reveal themselves in the way galaxies move, the way light bends, and the way the universe expands. This has inspired a vast network of experiments and missions across Earth and space. Detecting dark matter. There are three main strategies for detecting dark matter. Direct detection experiments. Scientists build ultra-sensitive detectors deep underground, shielded from cosmic rays, hoping that a passing dark matter particle might collide with an atom inside. Xenon Italy uses a giant tank of liquid xenon, waiting for faint flashes of light caused by rare collisions. Lux Zeppelin USA. Another powerful liquid xenon detector, one of the most sensitive on Earth. Superatoms Canada uses cryogenically cooled crystals to detect the tiniest vibrations from dark matter interactions. So far, no confirmed detections, but each experiment rules out possibilities and sharpens the search. B. Indirect detection. Dark matter particles might occasionally annihilate each other, producing detectable signals like gamma rays or neutrinos. Telescopes such as Fermi Gamma Ray Space Telescope scan the skies for these faint signs. C. Particle colliders. The Large Hadron Collider LHC in Switzerland smashes protons together at nearly the speed of light. The hope: collisions might create dark matter particles that escape the detectors, leaving behind missing energy. Again, no confirmed dark matter yet, but the hunt continues. Mapping dark matter with gravity. Even if we can't detect the particles, we can map dark matter using its gravitational effects. Gravitational lensing. As light from distant galaxies passes through clusters, dark matter bends it, creating arcs and distortions. By studying these, scientists build detailed maps of dark matter distribution. Weak lensing surveys. Projects like the Dark Energy Survey Day and Euclid mission launched 2023 are scanning millions of galaxies to create a 3D map of dark matter across cosmic time. These maps are crucial. They reveal how dark matter shaped the cosmic web, the vast structure of filaments and voids that define the universe. Probing dark energy. Dark energy is even harder to study because it doesn't cluster like matter. It affects the expansion of the universe itself. Astronomers use several strategies. Supernova surveys keep measuring distant explosions to track how expansion changes. Cosmic microwave background (CMB) satellites like WMAP and Planck measured tiny temperature fluctuations, giving precise evidence for dark energy's influence. Galaxy surveys. Projects like Sloan Digital Sky Survey (SDSS) study galaxy distributions, which encode information about cosmic acceleration. Future missions. Nancy Grace Roman Space Telescope NASA, designed to study dark energy using supernovae and weak lensing. Euclid ESA, launched to map billions of galaxies and pin down the effects of dark energy. DESI Dark Energy Spectroscopic Instrument, currently measuring the light of 35 million galaxies to map cosmic expansion in unprecedented detail. Why haven't we found them yet? The truth is humbling. Despite decades of effort, we still haven't detected a single dark matter particle or pinned down the exact nature of dark energy. Why? They may be far more elusive than expected. Our assumptions about their properties might be wrong. Or perhaps our theories of physics themselves need revision. Some scientists even suggest that dark matter and dark energy might not exist at all. Maybe instead, our understanding of gravity is incomplete. For example, modified Newtonian dynamics (MOND) suggests that at very low accelerations, gravity behaves differently, explaining galaxy rotation without dark matter. Emergent gravity. Eric Verlinde, a radical idea that gravity itself is not fundamental but emerges from deeper quantum processes. These alternatives are controversial, but they remind us science is not settled, it's alive, evolving, and open to surprise. The frontier of physics, the hunt for dark matter and dark energy, is not just about astronomy, it's about the deepest laws of reality. If we discover dark matter particles, it will open a new chapter in particle physics beyond the standard model. If we explain dark energy, we might unify quantum mechanics and general relativity, the two great but incomplete pillars of physics. In many ways, this is the next revolution in science, as big as the discoveries of relativity or quantum theory in the 20th century. A universe of shadows. Think about it. The very fabric of the cosmos is dominated by things we cannot see. 5% ordinary matter. Stars, planets, people, everything we've ever touched. 27% dark matter, the invisible scaffolding that holds galaxies together. 68% dark energy, the mysterious force tearing the cosmos apart. This is both humbling and awe-inspiring. It means that almost everything about reality lies outside human senses. Our eyes, telescopes, even our most advanced instruments capture only a fraction of the truth. It reminds us that knowledge is not static. What we think we know today may tomorrow seem as limited as the ancient belief that Earth was the center of the universe. Why it matters to us. At first glance, dark matter and dark energy sound distant, abstract problems for astrophysicists, not ordinary people. But in truth, they connect deeply to our existence. Without dark matter, galaxies could not form. Without galaxies, stars and planets would not exist. Without stars, life would not be possible. Dark energy determines the fate of the universe. Will reality itself endure forever or dissolve in a catastrophic ending? In short, dark matter made us possible. Dark energy will decide our future. We live in the shadow of these unseen forces, shaped by them, destined by them. The human spirit of discovery, the quest to understand these mysteries, is not just about physics, it's about what it means to be human. Throughout history, we have gazed at the sky and asked, where did we come from? What are we made of? Where are we going? Dark matter and dark energy are the latest, deepest layers of those same timeless questions. And though we don't yet have answers, the pursuit itself is valuable. Every failed experiment teaches us something. Every new mission sharpens our view. Every mystery forces us to think bigger, to imagine more boldly. The future of the hunt, the next few decades, will be revolutionary. Euclid Mission ESA launched 2023, already mapping billions of galaxies to unravel the cosmic web. Nancy Grace Roman Telescope NASA approximately 2027 will search for the fingerprints of dark energy with unprecedented precision. Lux Zeppelin Xenont Superatoms direct detection experiments that may finally capture a dark matter particle. Next-gen colliders, proposed machines could smash particles with enough energy to create dark matter in the lab. It is entirely possible that in our lifetime we will finally discover what 95% of the universe is made of. Imagine the day humanity finally sees dark matter, or learns the true nature of dark energy. It will be a turning point in history, one that future generations will look back on the way we look back at the discovery of fire or electricity. Philosophical reflections. The universe doesn't just challenge our science, it challenges our philosophy. Think of this irony. The universe is mostly invisible, yet we live in the small visible fraction. To us, light defines reality, but to the cosmos, light is just a minor detail. It raises questions. If 95% of existence is hidden, how much more could be beyond even that? Could our universe itself be just a fragment of something larger, just as a fish in the ocean knows only water? What does it mean to be real if most of reality cannot be seen? Such questions remind us that science and philosophy are not enemies. They are partners, each enriching the other. The poetry of the unknown. There is beauty in not knowing. Imagine the night sky if everything were already explained, every star catalogued, every force understood. Wouldn't it lose its wonder? Instead, the cosmos keeps secrets. Dark matter and dark energy are like cosmic riddles, whispers of something deeper. They invite us to keep searching, to remain curious. And perhaps that is their greatest gift, not just shaping the universe, but shaping our spirit of exploration. Conclusion: living with the mystery. We began this journey with a startling fact: 95% of the universe is invisible. We learned how dark matter binds galaxies, how dark energy tears the cosmos apart, how both shape destiny itself. Yet at the end, we are left not with certainty but with awe. The truth is, we don't yet know what dark matter and dark energy are. But that is not failure, it is the essence of science. To stand on the edge of the unknown, staring into the cosmic abyss, and still take the next step. As Carl Sagan once said, somewhere something incredible is waiting to be known. Perhaps that something is dark matter. Perhaps it is dark energy. Perhaps it is something beyond our imagination. Until then, we look up at the stars, we build our telescopes, we run our experiments, and we dream. Because the story of the universe is not finished. It is being written by us. And that brings us to the edge of the unknown. We've journeyed through galaxies, traced the invisible threads of dark matter, and felt the cosmic push of dark energy. Together, they make up 95% of the universe, yet they remain shrouded in mystery. Think about that: everything we see, every star, every planet, every mountain and ocean, even you and me, makes up just 5% of existence. The rest is hidden, waiting for us to discover. Science thrives not on what we already know, but on the questions that remain unanswered. Dark matter and dark energy are not just puzzles for scientists, they are reminders that the universe is bigger, stranger, and more beautiful than we can imagine. And maybe that's the true gift of the cosmos. It keeps us curious, keeps us searching, keeps us humble. If this journey into the unseen universe sparked your imagination, don't forget to hit that like button, subscribe, and tap the bell icon so you won't miss our next adventure into the mysteries of space. Drop your thoughts in the comments. What do you think dark matter and dark energy really are? Could they be new forms of matter, or a sign that we don't yet fully understand gravity? I'd love to hear your theories. Until next time, keep looking up, keep wondering, and remember, the universe is vast, mysterious, and full of stories still waiting to be told.